I'm Anil Kumar, and this video is for my IB student Joseph, who wants to understand concepts relating to lines in R2 vectors. So in this video, we'll discuss a couple of concepts. The first, we'll try to understand the concept of lines in vectors. Then we'll understand line in R2, that is two dimensions, x and y plane. Represent line using vectors. Draw closed triangle for vector equation of line. We'll see equation of lines in R2 in four different forms: vector equation, parametric equation, symmetric equation, and Cartesian or scalar equation. We'll also see how to find x and y intercepts and interpret parallel and perpendicular lines. So I assume that you have good knowledge about lines from whatever you've learned since grade 9. We'll continue from there, bridge the gap, and then move on to vectors. So let's begin with the very basic concepts of lines and how it relates to vectors. Okay, so basically we say line is set of, what is a line? Line is set of collinear points. Right. So when we say collinear, it means we're talking about in one direction, right? So all lie in one direction, in one direction. So strictly speaking, what I'm trying to say here is, let us say these are my points, correct? These are my points. So this is a set of points which are in one direction. So these set of points form a line. Some important things about these set of points is how many are there? We have infinite number of points. Correct? And does the line representing these set of points, is it kind of a dotted line? No, it's kind of a continuous line. Right? So what you really do is these points are all connected. And when you connect them all, what you get is a line which extends in both the directions, right? So that is the line we are talking about. So I hope this concept is clear about the line. So this is what we say line, and let me call this line as L1. Okay. Now what you learned so far is that we could write equation of line in different ways. So let me place this line on a coordinate plane. So xy coordinate plane will be the plane of our paper in this case. So let's say, let me just draw an axis here. We say that's our y-axis. And let me draw another axis kind of like this. So we say that is our x-axis, correct? So we call this as x-axis and this as y-axis. Now if I know a point which is on the y-axis, we call this as y-intercept, right? So that is the y-intercept. From this y-intercept, we can get equation of the line. And as you know, equation of line could be written as y equals to mx plus b, right? Where this point is b for us, right? And what is m? M is slope, which you had been saying rise over. So for the time being, let me assume this point B to be, let's say point B is y-intercept. At x equals to 0, we have y value of 1. Let's say this value is 1. Let's keep it simple. And to get another point on this line, what we can do is we can check, let's say we go 1, 2, 3 steps, and then we go 1 and 2 steps, we get another point on the line. So that really means to reach another point on this line, we can form a triangle whose rise is, that is change in y, which is 2 steps, and this is change in x, which is 3 steps. And therefore, the slope is 2 over 3. Now, since we know that the slope is 2 over 3, we could write equation of the given line as y equals to 2 over 3 x plus 1. Do you see that? So this is what you had been doing since grade 9 about the lines. And this line we say is being represented on a coordinate plane x and y. Correct? At times you have also represented this line in different ways. You could multiply by 3 and write it in standard form. So you have also represented the line in the form ax plus by plus c equals to 0. And some of you have also worked with this formula, x over a plus y over b equals to 1. And this slope formula could also be written as y minus y1 equals to m times x minus x1, right? That is from this definition itself. Rise is y minus y1, run is x minus x1. And then when you cross multiply, you get that formula. So all this you did so far while working with lines. Now let's extend this concept to vectors. Now in vectors, what really happens is we are again seeing the same line, the same coordinate plane, and we'll consider the same example. Now let's begin by the point 1, which is our y-intercept. Let me call this point as let's say A. So point A is 0, 1 for us. And in this case, we found that the next point we could easily get by adding the slope. Rise of 2, run of 3. So if I go to point B, which is, let us say, this point, then I can say point B will be the change in x, which is slope m for this particular line, is 2 over 3, right? 2 over 3. 2 is change in y and 3 is change in x. Do you see that? So the x value changes by 3, y by 2. So I could add 3 here and I could add 2. So if I do addition of 3 here and addition of 2, I get more points on this line. So I could get B as 3, 3. Similarly, I could get another point C. Adding 3 will give me 6 and 2 will give me 5. I could get another point D as 9 and 7. So I could get multiple points on my line using the concept which we learned. Now in vectors, we represent these set of points with the help of coordinate. So we can say any point xy, right, could be represented by, you can start from somewhere, right? Let's say you start from point B, let's say, or let's say point C. Let's start from point C. Let's take this point C. So in our case, C is 6, 5. So in this case, we can say we can start from 6, 5. And to get the next point, what do? We just add change in x and change in y, which is 3, 2. And to get more points, we add 2 times this, 3 times this. We could even add minus 1 times this, minus 2 times this, right? So those numbers are called scalar multiples, and we call that actually a parameter. And we normally represent it with t. So if I write like this, then it really becomes equation of this line in vector form, right? So we'll get into that details more, but to give you an idea, here we are saying t is our parameter. Now parameter is a new term. Line, you know how many dimensions does have? Line has? Line has only one dimension, right? So one dimension. SI1. Okay. One dimension is being represented by t, that is length. Correct? So how far are you from a point? Do you see that? So that is the value of t. We're representing so many units, so many times this unit. Do you see that? Kind of. So t gives you all the set of points on this particular line, and of course t should belong to set of real numbers. Do you see that? So that is how we get the concept of line in vectors. So in our vector space R2, if x and y are the coordinate planes, any point on the line could now be represented by a general equation. So let me write down the general equation for you, which will be xy equals to any starting point plus t times any direction AB. Do you see? This AB is called the direction number, correct? So we'll explore this further as we move along. So I hope till now you have seen how the line concepts which you learned so far are related with the line in our vector space R2, right? So let's move on, and now we'll represent this line using vectors, and we'll also draw a closed triangle, and we'll do a few more concepts on vectors. So let's continue with the same example. I'll redraw the line, and then we'll talk more about it. So that's the coordinate plane represented by x-axis and the y-axis. We'll draw the same line which we talked about. Let's say that's the line we're talking about, correct? And we are going to consider any general point on this particular line. So, well, the points on this line which we considered were kind of like this, was 0, 1. These are the coordinate points, right? 3, 3, 6, 5, and so on. How did we get these points? We said that the direction of this line could be represented by 3, 2, right? 3, 2. And that's how, by adding 3, 2 or multiples of these, we get different points on this particular line. That is what we learn. Now, when I draw a line as shown here, and when we are talking about two axes, x and y, we call this as R2, two-dimensional plane. And this line which is shown here is being represented on R2, right? Now let's see how to find the points once again. So let's say if I have a point here which is x0, y0 in general. So that's my point P. So I have a point P which is given by the coordinate x0, y0. And let's say the direction M for the given line is AB. So the direction is the vector A and B. Right? So what we're trying to say here is that you can find any other point on this line. Let's say we say in general xy will be equal to x0 plus y0 plus some multiple of AB, some multiple of AB. So you can get any other point. So when I write like this, we are relating set of points in R2, that vector space. Do you see that? Now, if I write this equation as an equation of a line, I could write this as R, equation of the line R, with this bar saying it's a vector. We could also write this in the coordinates like this, xy equals to x0, y0, a given point, plus t, the parameter t, in direction numbers A and B. Now, that is how I could actually represent my line, which is set of all the points. Now, in this case, t belongs to set of real numbers. So if I consider that point to be x0, y0, which I can say is my position vector, right? So when I write x0, y0, I'm saying if I draw a line with tail at the origin and head at this point like this. Now O is my origin. Then I'm saying that OP is x0, y0. Do you see that? That is called the position vector. Position vector, right? So from O, if we consider, it becomes a position vector. Similarly, when we talk about this direction AB, I could represent this direction also from the origin. You get an idea. So in general, if I draw a line parallel to this from origin, which is in our case 3, 2, that means you go 3 units, like 1, 2, 3, and 2 up, 1, 2. You come to this dot starting as a tail on the origin and head like this. So that becomes M 3, 2. Do you see that? So this, which is parallel to the given line, represents the direction for us. So we call that M, which now I have written as M1, M2, as my direction vector. Letters M1 and M2 are called direction numbers. So always a direction vector will be represented with tail on the origin and head pointing towards the direction of the line. You get the point, right? And from this equation, T, as you can see, is your parameter. So T is our parameter. Since line is single dimensional, we always have one parameter to represent the line. Okay, so I hope you got this basic concept. Now so we have represented the line as a vector. That's the line for us. And now we'll see how to draw closed triangle that represents vector equation. That's the vector equation which we want to represent with the help of a closed triangle. So in our case, let us take the point P as, going with this example, let's say the point is 6, 5. The direction is 3, 2. M is 3, 2. So from the point 6, 5, if I move in this direction, 1, 2, 3, 1, 2, I get to the next point. Do you see that? I go 1, 2, 3, 1, 2, next point. So all these points will lie on the particular line. So getting another point is actually a multiple of 3, 2, correct? So you could write x0 as 6, 5 plus the next point should be multiple t times 3, 2. And that will result into a new point, let's say x1, y1. So in general, I could actually represent this as a vector saying that from O to P, that is a position vector representing 6, 5. Is it okay? And then getting to the next point is t times, in general, 3, 2 for this particular case. So it is t times 3, 2. And what results is a point x1, y1, which I could draw like this. Do you see that? So that makes a triangle. That makes a triangle, correct? So let me redraw this triangle just to show you very clearly what we have done so far. So we had a line here. So we started with a position vector, OP. So that position vector, let's say, is this position vector, OP. So this is P, this is O. And then we moved along this line in this direction, that is. and the distance moved was scalar multiple of, let us say, m1, m2, to reach the final point, and this final point we could join from here, and we'll call this as Q. So from here, what we can say is that OQ is equal to, O to Q is equal to O to P plus T times M1, M2. Do you get an idea? So in vectors, we'll put them in like this, showing the vectors. So that becomes our equation for the line, and that is how we can relate a closed triangle and represent the vector equation. Do you see the relation? So in general, OQ could be any point, correct? So I could write this as xy, any point, equals to initial point x0, y0, plus t times any direction, m1, m2, correct? So that becomes, in general, a triangle which could represent the vector equation of your line. I hope the concept is clear, right? So now let's move on to the next topic. We have already learned the basic concept, and now we will see how to write equation of line in R2, and I'll show you in 3 different forms in this particular section how to write equation of line in vector form, parametric form, and symmetric form. In the next part, we'll take a scalar or Cartesian form, right? So let's talk about a general line now. So let's say that is the coordinate planes, and let me represent a line going like this. And let's take 2 points on the line. Line is always defined by at least 2 points or a point and a direction, correct? So that is how you define a line. Let us say that we take 2 points. One of the point is the starting point. We'll call this as x0, y0, and then we'll take another point Q on this line, and we'll say that is a general point xy. Okay, so these are the 2 points, and we will take M as the direction in which the line is moving, correct? So M becomes the direction in which the line is moving, so we can write this direction as M1, M2, right? So change in x and change in y, that is to say. So if I'm moving from, this is my origin, so OP represents the position vector for P, OQ represents the position vector for the point Q, and PQ is actually in the direction of M, and this PQ is actually equals to T times M, scalar multiple of that direction, correct? So that is what it is. So from here, what you get is that any point general xy as shown here, so equation of a line R, we can say is equals to any point in general xy should be equal to any given point x0, y0 plus t times the direction in which the line moves. So we'll call this as m1, m2, the 2 direction numbers. Is that okay? So this equation is called the vector equation, correct? So this is what we call the vector equation. So I'll call this as a vector equation. Now, I could actually rearrange this vector equation. All x values I could write as x equals to x0 plus t m1, and the y values I could write as y0 plus t m2. Now when I write like this, it still represents the same equation, right? X equals to x0 plus the component along x direction, and y as y0 and component along its y direction. Is that okay? Think like that. This type of an equation is called parametric equation, right? We'll call this as parametric equation. Mainly because we are writing each component in terms of parameter t. So t is the parameter, where t belongs to real numbers, correct? You should note that m is a non-zero direction vector, correct? If you have a zero vector, you don't know where the line goes, correct? Okay, so let me also write m is non-zero. Direction vector, or we can just say vector. Okay. Now, so that gives you a parametric equation. Now, what is symmetric equation? From this parametric equation, we can isolate t. So, if I use, let's reuse this equation. So, what I can do is, I have x equals to x0 plus t m1. I can take x0 on the left side, it becomes t m1, and then I can write t is x minus x0 over m1, correct? Similarly, I could also do for the y. So if we have y equals to y0 plus t m2, so we could write this as y minus y0 equals to t m2. Dividing by m2, we get t, the same parameter, right? So from these two equations, what can you conclude? Now, both these are writing in terms of t. So you can say that the parameter t is equal to x minus x0 over m1, and that should be same, right? Is also equal to y minus y0 over m2. So when I write the same equation in this form, it becomes what? Symmetric equation. Do you get an idea, right? So that becomes symmetric equation. So we are talking about the same line in different forms. Okay. A special case could be if m1 or m2 is 0, let us say, then we could take a special example. Let's do this. So I'm taking a very special case where I'm writing my line R, it is a special case. Or let's say we start with a point, let's say 2, 3 plus t times, let's say 1, 0. Now that really means that what kind of line do we have? It only moves in one direction, which is x. So if I have to represent this line, well, it's a very special case. As I said, we are starting with a point 2, 3, let's say 1, 2, 1, 2, 3, and it moves along the x direction. Next point is here, not along y, then here, then here. So what you land up with is a horizontal line. Do you see that? Now that becomes your vector equation for this line. As far as the parametric equation goes, you could write this as x is equals to 2 plus t and y is equals to 3 always. Do you see? Y is 3 always. Perfect. If I have to write this in symmetric form, how will I write? That's the question, right? X minus x0, so it is x minus x0 is 2 divided by 1 equals to what? Y minus 3 divided by 0. Now you cannot divide by 0, correct? But you observe that y is always equal to 3. So this is how you're going to write your equation in symmetric form. If one of the direction numbers are 0, you cannot divide by 0. So that comes when m1 is not equal to m2 is not equal to 0, right? So when they're not equal to 0, m1 and m2 are not equal to 0. However, if one of them is 0, you have to write like this, correct? So as an exercise, let me give you equations. So that is a question for you. If my equation is y minus 1 divided by 3, x equals to 5, write this equation in different forms, correct? So that becomes your exercise, and I hope you learn the concepts of how to represent a line in R2 as vector equation, as parametric equation, and as symmetric equation. In part 2, we'll have many examples, and part 3 will have a test on the same topic. Let's move on to the next part of the video and talk about scalar or Cartesian equation now. In previous part, you learned how to write vector equation, write it in parametric and symmetric form. Now we'll talk about Cartesian equation. The standard equation which you had been working with, like ax plus by plus c equals to 0, is actually the Cartesian equation in R2, right? We do not have any Cartesian or scalar equation in R3, but in R2 we do have this equation. In this part, we will see how to write vector or parametric or symmetric equation in terms of Cartesian equation, which is of this form. And we'll also see its significance, right? So let's take up an example to begin with. Let's say we're talking about a vector R, which I've been representing with xy as, let's take a point, let's say 5, 6, plus t times, let's say 3 minus 2. Okay. Now, in this particular case, I could write x as equal to 5 plus 3t, y as equal to 6 plus rather minus 2t, correct? Because this is negative. Now from here we can, that is the parametric form, correct? Now from here we can isolate t. So if I can isolate t, I can write t as equal to what? X minus 5 divided by 3, right? And from here I can write t as what? I can take 2t this side, or let me write t as equals to y minus 6 divided by minus 2. Is it okay? So as soon as I do this, it is symmetric form. So what you see here are 3 different forms, right? So this is the vector form. Now that one is parametric form. And this, both are equal, gives you symmetric form, right? Now see what happens. These two t's are equal, so I could write this as x minus 5 over 3 equals to y minus 6 divided by minus 2. If I cross multiply, I get minus 2 times x minus 5 equals to 3 times y minus 6, correct? Open the bracket, you get minus 2x plus 10 equals to 3y minus 18. Bring the terms together. Let's do it here. So we'll bring everything together, just make this positive. So we could write this as bringing them to the right side as a 0 equals 2. So we have 2x plus 3y minus 18, and that minus 10 gives you 0 equals to 2x plus 3y minus 28. Do you see? Now that is ax plus by plus c form. Do you see that? Correct? So what we get here is a form which is similar to that. Now this is called the Cartesian equation, right? This is called the Cartesian equation. Right, so this is what Cartesian equation is. Now we did all this to get Cartesian equation. Your question, which is very valid, is how do we get it from the given condition? In Cartesian equation, you will notice, let me go back to this equation, ax plus by plus c equals to 0. A and b actually represents normal to the line. These are normal to the line, So if I have a line which is kind of like this, I could have many normals, right? So this is a normal. Do you see that normal? Normal means it will make perpendicular to this. Now we got that particular equation. So what I'm trying to say here is, what is a normal to the line? Normal vector to the line is 2, 3. We were given the direction vector m as 3 minus 2. Can you confirm that this is a normal vector? How? That's the question for you. How? How normal is related with m? Well, the dot product should be 0, right? So if I get the dot product as 0, I know this is normal. Is that okay? So what I'll do is I'll find dot product of 2, 3 and 3, 2, 3 minus 2. So if you multiply, you get, the dot product, 2 times 3 is 6. 3 times minus 2 is minus 6. You do get 0. So the dot product is indeed 0. That confirms that 2, 3 is indeed normal. Do you see that? Correct? So that is how we can find the normal also. Now the question is again the same. If I'm given this condition, how do you write Cartesian equation? Well, if my direction vector is 3 minus 2, then to find normal, I just have to interchange and change one of the signs. So 2, 3. Since I know that normal is 2, 3, the Cartesian equation should be 2x plus 3y plus c equals to 0. How do I find c? I know the point 5, 6, so I substitute 5, 6 to calculate c. So if I write 5 here, I get 2 times 5, which is 10, plus 3 times 6, which is 18. So 10 plus 18 is 28. So that gives us c equals to minus 28. Do you see that? That gives us c equals to minus 28, and that gives us the equation. Correct? So what we see from here, that a Cartesian equation can be written as ax plus by plus c, where a and b are normal to the line. Given a vector equation or any other form of the equation, we can always get the Cartesian equation by using this concept in R2, right? Cartesian equations or the scalar equations, sometimes they are called as, represents line with their normal. I hope this concept is very clear. So let's move on to the next topic here, and that is to find x and y intercepts. Okay, let's take an example before moving forward. So let's have an example here. So what we will do is we'll consider equation of a line which goes through 2 points. Point A will take as 1, 4, and point B will take as 3, 1. Okay, so these are the 2 points on the line, and we'll try to write down vector equation, parametric equation, symmetric equation, and Cartesian equation for a line which goes through these 2 points, correct? Since we know the 2 points, we can always find the direction. So the direction vector will be from, let's say, A to B, right? So that should be 3 minus 1, that is x2 minus x1, and y2 minus y1, which is 1 minus 4, correct? Now that gives you the direction as 3 minus 1 is 2 and 1 minus 4 is minus 3. So that becomes the direction. Now how do I write the vector equation? So the vector equation will be what? Very simple. The vector equation is take any one of these points. So we say R is you can say could be represented as, you could write xy here. Any point on the line xy will be, let's say, starting with A, which is 1, 4. So that when I write in this form, it becomes a position vector, remember, plus parameter t in this direction, 2 minus 3. Do you get an idea, right? So 2 minus 3. So 2 minus 3. So you get an idea. Let's sketch this here. So let's say we have a point here which is 1, 4. So at 1 we have 1, 2, 3, 4. And then as you move along, 2 minus 3 means you move 1, 2 unit and 3 down. So 1, 2, 3. So get to the next point, correct? So when you join these points, you get your line. So joining these points in either direction, you get your line. Do you see that? So that is the line which we are talking about. Correct? If you have to draw a triangle, this becomes OP. Right? So this is O, this is in our case A, right? That's the point B. So OB is equal to, so we can say OB is equal to OA plus M times, in this case, directions 2, 3, 2 minus 3. Do you see that? That direction, 2 minus 3. So that becomes your representation in the form of a diagram, vector diagram. Correct? Now we will write this in the parametric form. So I could write x as equal to 1 plus 2t and y as equals to 4 minus 3t. Do you see that? Simple. If I isolate t, I could write it in the symmetric form. So I could write t equals to x minus 1 over 2. I don't even have to do this part from here. I could say point is 1 and 4. So y value is y minus 4. And the direction is 2 minus 3. I have to divide by minus 3. Do you see that? That becomes the value of t. So I could write this as x minus 1 over 2 equals to y minus 4 over minus 3. So that becomes your symmetric form, right? So this is symmetric form and that is parametric form, correct? How do I write in Cartesian form? So I've once again taken this mainly because I want to explain how to write Cartesian form. So when I know that the direction m is 2 minus 3, what is normal? I'll flip this, so I get 3, 2. And I will change one of the signs. Since this is negative already, I can change this to positive. So n becomes 3, 2. Do you see that? Now, since normal is 3, 2, in Cartesian form, sometimes we say scalar equation. I could write this as 3x plus 2y plus c equals to 0. Since I know 1, 4 is a point on it, which is point A, to get c, I'll replace x and y with 1, 4. So I can write this 3 times 1 plus 2 times 4 plus c equals to 0, right? So which is 3 plus 8 plus c equals to 0. And that gives you the value of c as equal to minus 11, correct? 8 plus 3 is 11. And therefore, the Cartesian equation is 3x plus 2y minus 11 equals to 0. Do you see that? So that is going with the normal, or alternately, you could also go from here, cross multiply, correct? So the second approach will be cross multiply. So if you do that cross multiply, you get minus 3 times x minus 1 equals to 2 times y minus 4. So when you expand this, you get minus 3x plus 3 equals to 2y minus 8, and that gives you the same equation. Do you see that? So bringing minus 3x to this side, 3 to that side, you get the same equation. So either way, you can get the Cartesian or scalar equation. So I hope this example helps you how all these 4 equations are related. Now we'll talk about x and y intercepts and parallel and perpendicular lines.